The Greek letter rho is used to denote the density of an object at a particular point. So rho at xyz is the density of the object at the point xyz. Now the density, or the average density of an object, is mass divided by volume. In other words, the mass is the average density of the object multiplied by its volume. Now the density could vary, so rho may not be constant. In that situation we have to consider tiny elements of volume, which include the point x, y, z. So this volume is dv. So, well, initially it would be delta v, but in the limit, as delta v goes towards 0, we use dv for the volume element. So we'd have to get the density at this point xyz and multiply it by the volume. So the mass element, which we could call dm, this is the mass of this volume element, is the density at that particular point xyz. It's not necessarily constant density, times dv. So this is a mass element of mass dm, and you know, if we want the total mass, we need to sum all of those mass elements. So in brackets here we have dm. So if we integrate dm, we have the total mass, which we could call capital M. So down here in the denominator we could write capital M for the mass of the entire object. Now I'll write dm here to emphasize that we are looking at an element of mass dm. Now we want to get the x coordinate of the center of mass of this object. To do that, we need to consider the moment of each mass element about the x-axis. We could actually think of the moment of the force of gravity on this mass element dm. The force of gravity would be vertically downwards, and we want the perpendicular distance of the line of action of this force, which is vertically down, to the y-axis. Well, that perpendicular distance is none other than the x value of the mass element. So I'm trying to indicate the x value here. So the line of action of the force is vertically down, and x is the perpendicular distance of the y-axis to the line of action of the gravitational force, which is related to the mass. The bigger they're proportional actually. If we double the mass, we double the gravitational force, or the weight of the mass element. Now we are not going to consider the weight. The weight would actually be given by the mass times g, acceleration due to Earth's gravity, for objects near the surface of the Earth. We're going to leave out that factor of g. It's going to cancel out anyway if we talk in terms of forces. So we can just forget about that and multiply the mass dm by x. Okay, but dm is rho times dv, so we multiply rho times dv by x. So that's dm's contribution, and we have, well, this particular mass element, but we have to repeat this for all mass elements that make up this object, and we have to take the sum of all those moments, so we have to integrate. We have a very similar formula for y bar and z bar. For y bar we are considering the perpendicular distance of the line of action of the weight to the x-axis, but we don't consider the magnitude of the force of gravity. We just considered the actual value of the mass element itself, which is dm. So the distance here is y. So we multiply dm by y, or rho dv times y, and we do that for all mass elements, and we sum all those contributions, and that's the numerator for y bar. The denominator is the same, it's the total mass of the object, capital M. And we have a similar story here for z bar. We multiply the z coordinate of the position of dm by dm. In other words, we multiply z by rho times dv. We do that for all mass elements, and we integrate. Again, the denominator It's just the mass of the object. If the density of the object is constant, in other words, the density is the same everywhere for any point x, y, z in the object, well, we can just take the row outside the integral sign above and below and cancel them out. So x bar simplifies down to the integral of x dv over the integral of dv. Now, the integral of dv is just the volume of the entire object. And again, we have similar formulas for y bar and z bar, we just cancel out. Let's look at this example. V is the tetrahedron bounded by the planes x equals 0, which is the yz plane, y equals 0, which is the xz plane, and z equals 0, which is the xy plane. We also have this plane x plus y plus z equals 4, or z equals 4 minus x minus y. Now we're going to start by getting its volume. Now we saw in previous videos that we considered lines, in a cross section of the object. Now we don't have a uniform cross section for this object. I mean, if we were to integrate from this point to this point here, where this line is parallel to the y-axis, that won't actually help us too much, because then we would have to integrate in this direction, in the z direction, and instead of getting what we want, we will get a rectangle, and we don't want a rectangle. See, if we take a cross section of the tetrahedron, we don't get a rectangle. We'll actually get a shape like this. Well, if I try to draw it a bit more accurately, it will look more like this. And that's not constant, of course. If we pick another line here, we get a different cross section. So we just have to be a little bit careful here about integrating. So it's not good enough to take a line in the xy plane, get its length. Well, actually, we can read off what its length is. It's 4 minus x. If we were to integrate from y equals 0 to y equals 4 minus x, well, integrate 1 dy, or I could just write dy from 0 to 4 minus x, we would get 4 minus x, as we've seen before. If we integrate 1, we get y. We apply our limits, we'd end up with 4 minus x. Okay, and then if we were to integrate with respect to z, we could find this point here. Depends on this line, of course. But if we do, as I said already, we get the wrong cross section. So a better approach is to take a point in, say, this face here. That's the face in the xz plane, and draw a line parallel to the y-axis until we hit this slanted face. Well, we know the coordinates of this point. The y value is 0. Okay, it's a point in the xz plane, but x and z can be anything we like. Well, as long, of course, as the point is in this face. We'll get back to that. Now we want the z value of this point to be the same as the z value of this point, because this line is parallel to the y-axis. Okay, so both of these points are the same distance above the xy plane. Now, we can't just put y here. This is not just any old point. Okay, this is a point on this slanted plane here. So we are constrained by that fact. So if it's a point on the plane, it's got to satisfy the equation of this plane. So if we make y the subject here, actually it's easier up here. Y equals 4 minus x minus z. And of course we have z here, same as this z. These z's are the same. So we are moving entirely in the y direction, so we're integrating from y equals 0 to y equals 4 minus x minus z. And we're integrating 1, of course, with respect to y. Well, you can leave out this 1 if you want to. Now we're going to get the correct cross section. It's a right angle triangle, as you can see. Now to do that, we need to imagine this line, moving in the z direction. So we will sweep out the area of this triangle. So we have to go from z equals 0 to whatever the z value of this point up here is. Now, how do we find that? Well, the equation of the plane is z equals 4x minus y. And this line has the property that all the y values on it Well, the y value of any point on it is 0. So we just set y equal to 0. Okay. This is a line that's in the plane, but all the y values are 0 for points on this line. So if we set y equal to 0, we just get z equals 4 minus x. So the upper limit is 4 minus x. So now these two integrals will give us the area of this triangle, which is a vertical cross section of this tetrahedron. It's a cross section that's parallel to the xz plane, and of course it depends on where we take that cross section. It's not constant, as you can see. Right, and finally then we would have to get the volume of the tetrahedron by integrating in the x direction. Okay, so if we imagine moving this cross section in the x direction, we can sweep out the required volume. So we're integrating from x equals 0 to this point here. So how do we find this point? Well, both z and y are 0. Okay, so it's a point in this plane. If we set z equal to 0 and y equal to 0, we get 0 equals 4 minus x, or x equals 4. So that's our upper limit. So we're integrating from 0 to 4. Now I'll go through this quickly because I've covered it in previous videos. If we integrate 1 with respect to y, we get y, and if we plug in the limits here, we'll end up with just 4 minus x minus z. Okay, and we want to integrate that with respect to z. From z equals 0 to 4 minus x. So we get 4z minus xz, because x is treated as a constant. If we integrate minus z, we get minus a half z squared. Now we plug 4 minus x in for z, and see here we have 4 minus x multiplied by z if I factorize out the z. So that's 4 minus x by 4 minus x, or 4 minus x squared. Now we have minus a half times 4 minus x squared. So we've 1 times 4 minus x squared minus a half times 4 minus x squared. That's just a half of 4 minus x squared. Now let's take the last integral. I'll write it over here. Integrating from x equals 0 to 4 of this thing here. I'll expand this out. I'll take the half outside. If we expand this out, we get 16 minus 8x plus x squared. And we have to integrate this with respect to x. Okay, this is straightforward. If you work this out, we end up with 32 over 3. Now let's get the center of mass. Let's start by getting the x coordinate of the center of mass. So we have the denominator. We've got the integral of dv, or the volume of the tetrahedron. That's 32 over 3. We have to integrate x with respect to v. So we have to replace this 1 with an x. If we integrate x with respect to y, we get x times y. Okay, and let's plug in our limits. So we've x times the upper limit. So that's going to give us 4x minus x squared minus xz. And if we plug in 0, we will get 0. So we have to integrate this quantity here with respect to z. So x is a constant, so we get the first two parts are just a constant. So we can multiply 4x minus x squared by z. Now integrating xz is going to give us minus a half x z squared. So we plug 4 minus x in for z. This is what we get. Now, to make life easier, we can actually take x out of 4x minus x squared, and we'll have 4 minus x times 4 minus x. That gives us 4 minus x squared. So 4 minus x squared appears twice here. So we can gather up what's in front of 4 minus x squared. That's 1x minus a half x. That's a half x times 4 minus x squared. So now for our last integral, we have to integrate with respect to x what we just found from x equals 0 to x equals 4. We can take out this half and we can square this out. We get x times 16. We get minus 8x by x minus 8x squared, and then we have plus x squared by x, that's plus x cubed. So if we work out all of this, we get 32 over 3. By the way, it's just coincidental that the x coordinate of the center of mass is the same as the volume. Now to get the y and z coordinates of the center of mass, we could repeat everything. You know, if we look to the formulas, we have to integrate y with respect to v to get y bar. To get z bar, we have to integrate z with respect to v. Now the denominator is equal to the mass. It's the same in all cases. Something that I forgot to do is I forgot to divide by the volume. Okay, so the integral of x dv was 32 over 3. The volume is 32 over 3. So x bar works out to be 1. Okay, as I said earlier, if we want to get y bar, we have to do this triple integral with y here. And if we want z bar, we have to put in z. Now, however, we can exploit the symmetry of this tetrahedron to find y bar and z bar. So, x bar is 1. Now, notice that each of these points is equidistant from this corner of the tetrahedron. Okay, these lines have the same length. So by symmetry, we would expect the coordinates of the center of mass to be equidistant from the origin. So we would expect y bar, well, we would expect y bar to be 1 also. And we would expect z bar to be 1. So the center of mass is somewhere about here. So we go a distance 1 here, and we go up a distance 1. So the coordinates of the center of mass are 1, 1, 1.